This section is Ethernet framing and introduces the basic role and operation of Ethernet technology within a network. Transmission over a physical medium requires rules that define communication behavior. The management of the forwarding behavior of Ethernet-based networks is controlled through IEEE 802 standards defined for Ethernet data link technology. A fundamental knowledge of these standards is imperative to fully understand how link layer communication is achieved within Ethernet-based networks. So upon completion of this section, it is expected that trainees will be able to explain the application of reference models to networks, describe how frames are constructed, explain the function of MAC addressing at the data link layer, and describe Ethernet frame forwarding and processing behavior. In terms of network communication, we tend to find that two sets of rules exist in the form of lower layer standards and protocols, such as the IEEE 802 standards that we see mentioned here, and upper layer standards or protocol suites that are effectively a collection of rules or protocols. An understanding of the difference between upper and lower layer protocols and the behavior of these protocols is critical to ensuring effective skills for designing, implementing, and troubleshooting networks. So through the course of this training, we shall build a firm knowledge of these standards and their role in supporting network communication. The lower layer includes separate standards for Ethernet-based networks that for the most part are considered to be in relation to local area networks, and alternative standards for transmission over wide area networks where a serial medium is used. Serial-based networks offer more variety of lower layer standards, which includes protocols such as frame relay, PPP, and HDLC. As such, these serial-based lower layer protocols shall be introduced as part of the intermediate course of this training. We shall therefore initially focus on the 802 standards for Ethernet-based networks. Upper layer standards represent another set of rules that are used to manage the logical forwarding and delivery of data. Many standards exist at the upper layer, including ISO, Novell NetWare, and IBM-based SNA standards, but TCP/IP is the protocol suite that has been adopted as the global standard, containing protocols such as IP, and therefore all topics discussed shall be in reference to this standard. In order to simplify the network communications architecture, various models were designed to break down the structure of networks. Each layer in this model represents a set of processes or responsibilities, and enables boundaries to be defined between these processes. As such, protocols will commonly be associated with a given layer. So in terms of the TCP/IP reference model that we see here, this consists of 4 layers, and we should understand that the TCP/IP protocol suite is primarily concerned with upper layer processes. The network layer is responsible for defining how traffic is logically forwarded between networks, while the transport layer is responsible for the end-to-end delivery of data, commonly employed to ensure delivery to the end station occurs successfully. The application layer summarizes the processes that support getting the data ready for the intended application and delivery to that application, such as in the case of delivering an email to the inbox of a currently active mail account. In terms of Ethernet, however, the TCP/IP model summarizes all processes that relate to the IEEE 802 standards for Ethernet and other lower layer protocols, and references these as being part of the network interface layer, since lower layer protocols are not the focus of this model. A more common alternative to the TCP/IP reference model is the OSI reference model that represents the ISO-based model of architecture for open systems interconnection in relation to the ISO standard protocol suite that was briefly introduced. So due to the clear and effective breakdown of network processes, the OSI model is commonly used to reference processes not only related to the ISO standard, but also in support of TCP/IP. So as we can see here in the case of this OSI reference model, it consists of 7 layers. The application layer represents the logical interface through which data is sent to the intended application. The presentation layer in this case is separated from the application layer and concerns with ensuring the data format can be interpreted by the application on delivery, and so is responsible for translation of formats both to the application and over the network. The session layer handles sessions that occur between endpoints in the network and generally involves processes that ensure sessions do not experience issues that cause sessions to break down. An analogy of this would be an event manager who oversees the setup of an event, ensures its smooth procession, and finally handles the event's closure. As such, the session layer has a close relationship with the transport layer, which often represents the embodiment of such an event. The transport layer and network layer represent the same processes as found in the TCP/IP reference model. The lower layer processes within the OSI reference model have been broken down to distinctly separate the processes that represent how data is carried onto the link, such as is found with CSMA/CD, and how end stations on a segment interpret the received data, and separate these from the physical medium, connectors, and voltage in the case of Ethernet that represents the physical transmission mechanism of signals. These processes fall under the data link layer, while the physical components fall under the physical layer. So as we've explained, each layer has a role in the processing of data, such as translating the data format, as in the case of the presentation layer. Processes also involve the adding of instructions to the data to determine how the data should be processed as it is carried between the source and intended destination. So we demonstrate here a typical example of encapsulation in which instructions are prepended to the data, which in turn results in an increase of the overall data size. Instructions can only be processed by the corresponding layer. For example, instructions added at the transport layer will only be processed by the equivalent transport layer protocol at the destination. To all other layers, these instructions are viewed as unintelligible data. The maximum supported data size within the TCP/IP protocol stack is 1500 bytes, and therefore the amount of data carried in each data block must be determined before instructions are added. So once the TCP/IP encapsulation is complete, the data block cannot exceed these 1500 bytes. But this does not include the encapsulation performed at the data link layer, since this layer is controlled by other standards such as Ethernet, and so commonly we will see a final data block size of around 1518 bytes after the 18-byte instructions of Ethernet are added. So the final stage of this process following encapsulation sees the data converted for transmission over the physical medium. Following encapsulation at the data link layer, the data will include instructions to support transmission and processing as the data is carried over the network and reaches its destination. The data in each stage of encapsulation is referred to as a form of protocol data unit, or PDU for short. The data in this form, following the data link encapsulation, is referred to as a frame, for which the lower layer instructions are used to identify whether the data has reached its intended destination within the local segment. So we show here a single segment on which two end stations are located to demonstrate this process. The frame header is used to ensure the transmitted frame can be received, while the trailer ensures that the integrity of the frame is maintained and has not experienced errors during transmission. For Ethernet, the frame encapsulation may use one of two formats. The format that is used depends greatly on the protocol used to perform encapsulation at the upper layer. So we shall introduce the details of this process in the following slides. One of two frame types will be applied to data that is carried over Ethernet networks. As mentioned, the frame type depends greatly on the upper layer protocol that added instructions to the data prior to the data being received by the link layer. These two frame types are known as Ethernet 2 and IEEE 802.3. The format of the two frames are similar in that both contain source MAC, destination MAC, and frame check sequence or FCS fields. However, they vary in the case of one field, which in the Ethernet 2 frame represents a type field, and in the IEEE 802.3 standard represents a length field. The details of these fields shall be explained as we progress. In the case of the type field, the lower layer Ethernet protocol is able to determine the protocol to which the data is to be forwarded once processing by the Ethernet standard is complete. For the IEEE 802.3 standard, the length field only details the length of the frame and so relies on an extended set of instructions referred to as 802.2 LLC or logical link control that is used to determine the protocol to which the data is to be forwarded after processing by the IEEE 802.3 standard is complete. Not all protocols are supported by the 802.2 LLC header, and therefore a subnetwork access point or SNAP header is employed to support these additional protocols. So each protocol is associated with a type value that is usually represented in a hexadecimal number format. However, for now, we can simplify this into decimal numbers. So if the type value of the protocol is greater than or equal to 1536 or 0600 in hexadecimal, the Ethernet 2 frame type will be used. If the type value is less than or equal to 1500 or 05 DC in hexadecimal, the IEEE 802.3 frame type is used. We give an example here to demonstrate how the Ethernet 2 frame type is applied, and we shall use two common protocols to demonstrate this. We can start off with the Internet Protocol, or IP, which is represented by the type value of 0800 in hexadecimal, which for easier understanding we can represent using the number 2048. Since this type value is greater than 1536, the encapsulation process will apply the Ethernet 2 frame type at the data link layer. Another common example involves a protocol known as the Address Resolution Protocol, or ARP. This protocol is represented by a hexadecimal value of 0806, which we can simplify to a value of 2054. Again, since this value is greater than 1536, the Ethernet 2 frame type is used. So we shall introduce the protocols mentioned here in more detail as we progress. In the case of the IEEE 802.3 frame header, we can again demonstrate its application through the use of another protocol referred to as the Spanning Tree Protocol, or STP. So in this case, STP is represented by a value of 3, which is lower than 1500, and therefore means that in the case of this protocol, the IEEE 802.3 frame type is used. So we shall also introduce the Spanning Tree Protocol in more detail as we move on. It should be noted also, however, that the Spanning Tree Protocol is also a form of data link layer protocol, meaning that lower layer headers do not necessarily only reference protocols of the upper layer, such as IP, as based on the OSI reference model. So one final thing to note is that the type field for the IEEE 802.3 frame is carried as part of the snap header. Ethernet is a form of multi-access network, meaning multiple end stations can be located within the same segment. We simplify that here by showing two end stations connected to a single Ethernet segment. In any case, however, it is important that each end station can be uniquely identified, so that when data is transmitted over the segment, only the intended recipient will receive the data. In Ethernet networks, this is achieved using media access control, or MAC addresses. The MAC address is a unique address that is assigned to each network interface on an end system to uniquely represent that interface on the Ethernet segment. Data sent from a sender to a destination will reference the intended recipient on the local segment by including the MAC address of the intended recipient in the destination MAC field of the frame header. The sender will also include its own MAC address in the source MAC field to allow the receiver to know where to send any reply. Every MAC address represents a unique value that is assigned to represent each individual interface in a network segment. The MAC is composed of a 48-bit address that is divided into two parts. The first is an organizationally unique identifier, or OUI, that is requested from a numbers authority that assigns a range of MAC addresses to an organization. A single organization may be registered as having multiple ranges of MAC addresses, especially if the organization manufactures products that utilize MAC addresses. The second part represents the range of addresses assigned based on a particular OUI, which equates to over 16.7 million addresses. These addresses are therefore expected to be unique for every individual interface to prevent two devices in the same segment from receiving and possibly responding to a transmission intended for a single destination, in the same way that two school children with the same name in a class may mistakenly both reply when their name is called by a teacher. Frame forwarding is achieved using one of three methods. Unicast represents the first of these methods and defines transmissions sent from a single source to a single destination, even in cases where multiple devices are connected to the same segment, as is common in multi-access networks such as Ethernet. The 8th bit in the most significant octet, or the first byte as it may also be known, is always set to 0 for unicast, to represent that it is intended for a single destination only. In a shared collision domain, as we can see shown in this example, all connected hosts will receive the physical transmission. However, the frame will only be processed by a single recipient, which in this example is host B, while all other hosts will generally ignore the received frame, since the listed destination MAC address of the frame differs from the interface MAC address of all other hosts. The second method of frame forwarding is broadcast and involves the transmission of a frame with all 48 bits of the destination address being set to 1, which in hexadecimal is represented as a string of F values as we see in the example. This effectively means that all hosts on the network segment are intended recipients and as such are expected to process the frame accordingly. The example demonstrates a broadcast transmission at the data link layer by host A, followed by which hosts B, C, and D on the same segment all process the transmitted frame once it is received. The third method is known as multicast and can be understood as a form of selective broadcast. This involves hosts listening for frame transmissions on the local segment that contain a specific multicast MAC address as the destination address. Hosts that are listening for frames that have a certain multicast MAC address will process these frames as they are received. Hosts that are not listening for multicast traffic associated with a certain address, as in the case of host C in this example, will refrain from processing any received multicast frames. The 8th bit of the most significant octet in the multicast frames is set to 1 in order to identify that the frame is part of a multicast MAC address range, and so is distinguished from unicast MAC addresses for which the same bit is set to 0. In the previous section, we introduced the concept of collision domains and the potential for collisions to occur within a shared collision domain. As such, a process of collision detection known as CSMA-CD was introduced. We show here how this CSMA-CD operation is applied to the forwarding of frames in order to reduce the chance of collisions occurring in a shared network segment. We should understand that as frames are transmitted, they are effectively received by all hosts. However, the host will decide whether or not to process the received frame. Prior to transmission of a frame, a host will listen for frames being transmitted. This represents the carrier sense process of CSMA-CD. In the example, we can see how a frame sent by host C to host B is effectively also received by host A, thereby causing host A to wait before transmitting its frame. Once host A is confident that the transmission medium is clear of physical transmissions, it will attempt to transmit frames, which in this case are destined for host C. In cases where the transmission medium supports wire pairs for transmission and receiving, the potential for collisions is considered non-existent, except in the case where a hub device may be used. And so over such media types, carrier sense and collision detection is not required. Following transmission, a frame will be received by one or multiple hosts. It is then the responsibility of each recipient host to determine whether the received frame has reached its intended destination. The receiver will determine this by analyzing the destination MAC address within the frame header. It will compare this to its own MAC address for the interface and any MAC addresses it is currently listening for. If there is no match, the frame will be promptly discarded. If the frame destination MAC does match the MAC of the receiver, the host will determine the integrity of the frame using the frame check sequence value. If this check fails, the frame will be discarded. Frames that pass this check will be sent to the next protocol for processing. In this example, the next protocol is the upper layer internet protocol, or IP. This is determined by the type field that contains the 0800 hexadecimal value associated with IP. The frame header and FCS trailer are then discarded before the data content of the frame, which includes an IP header, are passed to IP for processing. In summary for this section then, it is asked, how does Ethernet determine the protocol to which a processed frame should be delivered? Well, frames carried over Ethernet networks contain a type field that is used to reference the next protocol to which data is to be sent for processing. So we have given a couple of examples in this section in the form of IP and ARP. How is it determined whether a frame should be processed or discarded upon being received by an end device? Well, receiving host will analyze the destination MAC address in the frame header to determine whether the frame is truly intended for the host. If the MAC address of the host interface and the MAC address in the destination MAC field of the frame header do not match, or is not a multicast address that the host is listening for, or the frame destination MAC is not a broadcast address, the frame will be discarded.